Nonparametric regression.
Yeah.
The floor is yours.
Yeah, thank you. So first of all, I'm very pleased to be here to present this talk. This subject on Minimax-optimal and locally adaptive online nonparametric regression. My name is Paul, and I'm a PhD student at Sorbonne University in Paris. So this is a joint work with my two amazing PhD advisors, Pierre Gaillard, who is somewhere in the room, and Olivier Wintenberger. Okay, so let's begin with the setting of the talk. The problem is the one of online regression with individual sequences. So the game protocol is as follows. At each round T, a forecaster or an algorithm observes an input xt from a subset X of RG. Then it chooses a prediction given the input xt, so hat ft of xt, which is a real value. Then it incurs a loss based on the prediction LT of hat ft xt. And then, given observed gradients and the losses, the learner updates his prediction function from hat ft to hat ft plus 1. The goal is to minimize the following quantity, which is the regret, given the function f belonging to some general nonparametric function set, big F from X to R. So the regret is the difference between the cumulative loss of the forecaster and the one of the function you want to be compared. Okay. So the difficulty in the individual sequences scenario is that you do not have any stochastic assumption on the data, xt, rt. So we are concerned with guarantees on our predictors, f1 to f big T, to hold uniformly over all data sequences. Okay, so the assumptions on the talk are as follows. So the losses are general convex losses. We assume them to be J-ellipses with some G known. X is a bounded compact subset of RG. Let's take it to be 0, 1 to D. And F is some bounded class of function with some B which is known also. And for this talk, we will focus to the set of alpha order continuous functions where alpha is between 0 and 1. And L, so both of these parameters are unknown. Okay, so now let's talk about our first contribution. So we propose a parameter online learning method that leverages a chaining tree structure. So what's a chaining tree structure? I put some drawing here. It's just basically a tree which is partitioning the subset X, and each internal node has 2 to the D children. So it could be, you could see this as very complicated, but as you can see also with the drawing is that whenever the chaining tree has to do a prediction at each time, you only need to, so it predicts only with the sum of the nodes along the path given the data X. Okay. So the results we get is as follows. So given any function f in the set of function of alpha order continuous function, we get this rate, sorry, which is scaling with linearly with the Lipschitz constant, the order constant, sorry, LF, given the sorry, what happened? Okay, sorry. So which is scaling linearly with the regularity constant order constant L, given the given competitor you consider. So you have also, we recover also the different regimes which are very classical and has been first presented in this paper of Hacklin in 2014 and 2015. So the new thing here, especially, is that we are both adaptive to L and alpha. And as I suggested with the drawing, is that our algorithm is also computationally tractable since we have only locked it over the parameters to update each time step. Okay? So now let me give you some intuitions behind the algorithm. If we decompose the regrets into two parts, which are a part with an estimation regret based relatively to some hat FM, which is the better chaining tree to achieve the problem, and the second part, which is an approximation regret regarding the ability of the best chaining tree to approach the given function f. The algorithm aims to make a trade-off between these two quantities. So as you can see, the specific structure of the chaining tree is crucial here, since all the nodes are aiming to correct the preceding one. And since we are trying to recover, a regular function which is alpha order continuous, we have the control of the decay of the coefficient, which is of order L to minus alpha m. We can then control the estimation regret of each node, since we are learning each node by a parameter-free subroutine, which has regrets, very specific regrets, but depends optimally on the norm of the competitor theta. And also we are able to control the approximation regrets. And so we just have to balance and to find the correct depth to balance the two terms between estimation and approximation. Okay, so the second contribution, let me ask a question to motivate this second contribution. We saw in the previous regrets that the algorithm was paying linearly the constant L. So the algorithm adapts it, but linearly, and pay it linearly. One question that arises from this is, could we do better if, for example, if we have low variation regions of the function, we would like to pay it less, and maybe where the function has high variations, we would like to maybe approximate it better and to balance the regrets again. So, sorry. So here we propose an algorithm that optimally competes against any pruning. So to explain what is a pruning, typically, I'm sorry. So typically here, each pruning is associated with a partition of the subset X of RD. And so we base our predictions here on what we call a core tree, which is typically an expert tree where each node now is a chaining tree which aims to approach locally the function we want to recover. So here what we see is that the algorithm is making a trade-off between the computationality with the square root of t times the number of nodes of the pruning you are considering, and a local regret, which is relative to the approximation regrets we had with the chaining tree. So here we also have the adaptivity, but now to local irregularities ln f. We could also have adaptivity to the smoothness rate alpha with respect to the node of the pruning. What we have also is the adaptivity to the loss curvature, improving the complexity you pay only the. You don't pay now the if the algorithm is facing X-concave losses, you reduce the regret term, which is related to the tracking of the best pruning, only to the number of nodes of the pruning you are considering. And so yeah, we finally managed to pass from global to some local some local regret. Okay, now if we come to this corollary from the previous results, so what we see in the first line of the table is that in case we the environment reveals losses that are f-concave, our algorithm achieves the minimum between a trade-off between paying L with a higher dependency or achieving time rate which is slower. No, not slower, sorry. A trade-off between a higher dependency with L but going very fast in time and paying more in time but with a lower dependency on the Lipschitz constant. And so these results improve previous one. So from this paper in 2020 and the other one from 2007. And I put some graphs here to explain on a synthetic regression setting on a toy example. So what we see here, the red curves is for the second algorithm, which is locally adaptive. What we see is that below under a regime where the Lipschitz constant, the order constant is too high, the algorithm is achieving a lower regret with respect to L. So you have L here on the X level. So both for the X-concave losses and for the F-concave losses and the convex losses. And what you see also is that if the constant L is too high, the algorithm will converge to some regime here, which is equivalent to BT, and won't try to adapt locally since the constant is too high. And that's it.
Again, we have time for 2 questions. I have one. So when you mentioned like the computational efficiency, I imagine that this is like in terms of number of some oracle requests, like, because for nonparametric it would be quite hard, right? Like,
yeah, but here the point is that the point is that each round, so in this case, we have to update only the depth, the number of nodes which is equal to the depth of the chaining tree, and especially with this structure, which is good, is that we only pay this number of nodes in complexity. Like,
D is the better, right?
Sorry?
Because it's one over D, right?
Yeah, it's 1 over D. So it's decreasing with the dimension. This is quite decreasing with the dimension, since intuitively the minimax rates we have here deteriorates exponentially with the dimension. And so
dimensions, you just need less to do because the rate.
Yeah, exactly.